Hi, everyone. I'm Swapnil Bhatia. I'm a computer scientist at Catalog Technologies, a DNA computing startup based in Boston. And I'm really grateful for this opportunity to present at FAST 2022 and I'm excited to tell you about DNA-based data storage and computing. So at Catalog, we're building the world's first commercially scalable DNA-based data storage and computing platform. So we use physical DNA molecules to encode digital data. Our mission really is to help preserve and extract information from all of the world's most valuable data archives. If you think about it, the next big breakthrough in science and technology will come from data that's stored away in some tape archive in some remote data center. And so it's imperative that all of that data is secure, readable, searchable, and computable, not just for the next year or 10 years, but hundreds or thousands of years. And so since our founding, we've focused on this problem of writing high-value archival data in such a way that it fits in the palm of your hand and is computable and accessible and doesn't really live in some large and expensive data center. And so DNA is a great medium for such dense storage of information. DNA is hyper dense. It's about 1 million times denser than any flash storage. It's massively redundant. You can easily and cheaply make copies, thousands of copies of DNA, 1,000 copies of a data set. It's ultra persistent, so you're able to read the genomes of extinct organisms precisely because the DNA that encodes that information is robust and stable, even after thousands of years. But even beyond storage, you can think of creating a chemical computer that accesses the information that's stored in the DNA archive, similar to the way every cell in your body is transcribing information from the DNA and making decisions. So similarly, you could leverage chemistry in order to operate on the information that's stored in the DNA archive. A unique feature of this archive, of this kind of computing, would be that it would be in memory or in storage. You wouldn't have to move data from a cold tier to a warm tier. Now, if you think of writing data into DNA, a natural way to do it is to define a dictionary where you map letters ATCG to 2-bit strings 0001 and so on. And then you grow this DNA molecule base by base. The problem with this approach is that to append a new base, a new letter, is really slow. It takes of the order of tens of seconds to write a new letter. And it's also very expensive. You can parallelize this approach. You can grow about 1 million such polymers in parallel. But even then, if you do the back of the envelope calculation, this approach just is too expensive and too slow. It doesn't scale to terabytes or petabytes of information. So at Catalog, we've come up with an alternative way of doing this. We start with a DNA data structure that looks like a binary tree, except that it's ordered, meaning at every level, the branches have a certain fixed order. So the red branch comes before the blue branch. And then we extend this ordering to a lexicographic ordering over all the paths in this tree. So this gives us pretty much a linear ordering of all the paths. And then we treat this linear ordering of paths as a linear address space to which we could write data. What makes it a DNA data structure is that we associate with every level of this tree a set of DNA components. So these are physical DNA molecules that all have distinct sequences, and they're designed in such a way that that DNA components in adjacent layers can concatenate with each other. So one can concatenate with two with three, and so on. And so we could take the Cartesian product of all of these layers and create a combinatorial address space. And this address space is one-to-one correspondence with the paths that I just described before. So how do we use this data structure to write data? So suppose we wanted to encode this bit string, this arbitrary bit string of zeros and ones, then we align it against our combinatorial space or against our data structure. And we identify the positions at which we see a 1-bit value. So for example, position 2 and 3 have ones. And so what we do is we assemble these specific DNA molecules that correspond to the positions that have 1-bit values. And in this way, if we were to take this sample, this subset of DNA molecules, and sequence them, then we would be able to reconstruct this bit string because every molecule in the sample points to the position at which there was a 1 value. So in this way, we could reconstruct the entire bit string. The cool thing about this approach is that using only 10 components, total 10 DNA pieces, we're able to construct a 32-bit DNA hard drive. In general, this scales really nicely. With L layers and N components, we can create an N to the L bit DNA hard drive with only L times N pieces of DNA. So if we wanted to write a terabit of information, 10 to the 12 bits, we could create a 12-layer tree with 10 components in each layer. And in that way, write a terabit of information. Now, if you go back to the base by base version, you would have to write a 500 billion bases. And that would be very slow and expensive. In our case, all of these DNA components, their sequences are completely decoupled from the data that we're writing. So we could prefabricate these DNA components and buy them in bulk and start stitching them together when we're actually writing the data. And this is the reason why our scheme has the potential to be millions of times cheaper than base by base writing. This whole scheme relies on being able to build these molecules on demand and really, really fast. And so that's possible too, because we could set up a reaction that concatenates these DNA components to form this molecule or any of these molecules as fast as we can pipette them into a reaction. And so to that end, we've designed a megabit per second writer that does precisely this. Our writer is capable of co-locating any of the DNA components into a reaction and building any molecule in our combinatorial space on demand. Using this writer, we're able to encode at about 18 megabit per second capacity, 18 megabit per second throughput. And this is scalable to gigabit per second future capability. So here are some initial results. This is only kilobyte scale writing. The x-axis shows 5 such runs. The y-axis shows the signal to noise ratio that we measured. The 2 groups of runs show that we can tune our codec with certain parameters so that we can achieve the signal to noise ratio that we're looking for. And in this way, we're ready to scale this to terabyte and beyond. So I'll stop there. I'd be happy to take any questions. You can see that this is a joint team effort. And so at Catalog, we're all really excited about this technology and would love to hear your feedback. Thank you.